In this practical, we're going to be investigating the presence of an electric field in a wire, and this device here is the wire that I'm talking about. So we've got a difference in electrical potential or of 2 volts between here and here. This power supply here is doing the job there. It's connected there to a direct current, so electricity is actually passing through that wire. But what it means is that there is in fact an electric field going right along the wire, and that's responsible for the movement of the charges through the wire. Now, what we're going to do is measure the electrical potential in volts, or potential difference in volts, along the wire at different intervals. So, and we're measuring the potential difference between this point here and the different points along the wire there. So I'm going to start. I've got a multimeter here that's set up as a voltmeter, and I'm going to assume that here, right at the start, the potential difference between here and here would be 0. So I'll then connect this to a distance of 10 centimeters along the wire, and you can see that there, and the voltage there is fluctuating a little bit, but let's call it 0.17. That's at 10 centimeters. So I'll adjust it now to 20 centimeters. So there it is at 20 centimeters. And if we have a look at the voltage or the potential difference, we can see it's 0.35. I'll adjust this now to 30 centimeters. And if we have a look at the potential difference measured in volts, we can see that it is 0.5. Again, I'll adjust the lead here to 40 centimeters, measure the potential difference, and you can see there that it is 0.68. there at 40. Again, moving it to 50. What I've got is a potential difference of 0.84 to 60 now. And the potential difference there is 1.02. Moving along now to 70. So there's 70, and if we have a look at the voltage or the potential difference measured in volts, that is 1.17. Adjusting the voltage now to 80. And there you can see that the voltage is 1.34. Now adjusting it to 90 centimeters. And looking at the voltage, the potential difference, we can see there that it is 1.51. Moving the pointer here along to, or the conductor along to the 100 centimetres by plugging this in to the plug at the end, we can have a look at the potential difference there, and our potential difference measured in volts is, as you can see, 1.72, and there you can see that we've got a potential difference of 1.75 volts. So now you're in a position to create a graph of voltage on the y-axis and distance on the x-axis, and we can have a look at the gradient.
So here are our results. We've got distance down here, potential difference there, and our graph over here. So we've got distance there along the x-axis and potential difference there along the y-axis. We've got a line of best fit here, and we've set the y-intercept to 0. And we've got the equation up here. Now, what does this equation, or more particularly, what does the gradient represent? The answer to that is that it represents the strength of the electric field along the wire. Let's have a look at a diagram. So here you can see a piece of wire, or the length of the wire if you like. We've got the voltage here, or potential difference there, and the distance there. And what we've done is we've found that the ratio of the potential difference to the distance right along the wire. What that gives us is the intensity, the strength of the electric field, the force per unit coulomb acting on the electricity that's there. That figure inside a wire is not a significant one. What is more significant is the application of this idea to parallel metal plates. Here you can see we've got a potential difference between the top and the bottom plate. And what that does is it creates an electric field between the two plates. That field, A, happens to be uniform, and B, varies with the potential difference and the distance. You think of it, increasing the potential difference here. That's going to strengthen the field. If we increase the distance, if the top plate went up here, this distance down here would be increased, which would decrease the intensity of the field. The unit for the strength of an electric field can either be volts per meter or newtons per coulomb. These two, volts per meter, newtons per coulomb, equate to being the same. We can check that by having a look at the dimensions. This device here, where we're looking at the intensity between two parallel plates, was very important in the development of the television, the old-fashioned television, and the cathode ray oscilloscope.